Imagine if you could take an elevator from Earth all the way to space. How revolutionary would it be to press a button and ascend straight into the cosmos? Just like going to the top floor of a skyscraper. It might sound like a dream from science fiction, but in fact, this space elevator is a concept that real scientists and corporations are seriously researching. Is it truly possible with 21st century technology, or will it end up as just another fantasy? Today's topic is the space elevator. Arguably, one of humanity's ultimate dreams. We will explore it from various angles, from its history and physical principles to its engineering challenges and future scenarios. Let us take you on an intellectual adventure, exploring the space elevator by looking at both the story-like dream and the reality that stands in its way. We will get to the heart of this magnificent concept. First, let's start with the birth of the idea. When and how did the concept of a space elevator emerge? Let's unravel its history. In our first chapter, the birth of the space elevator concept, the idea of a space elevator didn't just suddenly appear in modern times. Its roots trace all the way back to the late 19th century. In 1895, Russian scientist Konstantin Tsiolkovsky, inspired by the Eiffel Tower, published an idea for a tower extending from the ground into space. He dreamed that if there were a colossal tower reaching from the Earth's surface to geostationary orbit, we could overcome gravity. Geostationary orbit is an orbit approximately 36,000 kilometers above the Earth's equator, where an object revolves at the same speed as the Earth's rotation, making it appear stationary. At the time, neither the materials nor the technology was available, making it nothing more than a fantastical stairway to heaven. But the idea itself was groundbreaking. More than half a century later, in the 1960s, Soviet physicist Yuri Artsutanov proposed a more realistic concept for a space elevator. Artsutanov published his idea of a celestial railway in a magazine, suggesting a cable be lowered from a geostationary satellite to the ground. It garnered attention as a safe and efficient means of space transportation that could replace rockets. At the time, this idea was quietly discussed only within the Soviet Union. But some scientists were thrilled by the thought that it might one day surpass rockets. It was the science fiction author, Arthur C. Clarke, who made this ambitious concept world famous. In his 1979 novel, The Fountains of Paradise, he featured the space elevator as a central theme, introducing this dream to countless readers. In the story, a tower extending to the heavens is built on an island at the equator, and people travel to space using an elevator. Clarke's depiction was so vivid and realistic that it made readers wonder if such a future could truly come to pass. The space elevator instantly became a star in the world of science fiction, a symbol of humanity's future. This concept also had a significant impact in Japan. In fact, Japan is one of the countries with a particularly high level of interest in the space elevator. This is partly due to the discovery of a new material called carbon nanotubes in 1991 by Japanese scientist Sumio Iijima. This discovery excited researchers around the world with the possibility that a material strong enough for a space elevator cable might finally exist. Japanese researchers also have a high level of expertise in robotics and nanotechnology, giving them a major presence in the field of space elevator research. For instance, the major construction company, Obayashi Corporation, was quick to form an internal project team to seriously consider the feasibility of this dream. The space elevator has also been depicted in anime and manga, making the image of an elevator to space familiar to the general public. Its cultural impact cannot be overlooked. The space elevator has fired up people's imaginations as a dream that surpasses rockets. Rockets are high-cost vehicles that produce massive pillars of fire and are discarded after a single use. In contrast, an elevator is a reusable, quiet, and safe mode of transportation. The ultimate link between the Earth and space. In the 20th century, humanity achieved a moon landing, and the next great dream was a bridge directly connecting the ground to space, the space elevator. While some laughed it off as a fantasy, other scientists believed it would one day be realized. So, is this incredibly grand plan theoretically possible? In the next chapter, let's explore the principles and structure of the space elevator. Is it theoretically possible? The structure of the space elevator. Let's visualize the basic structure of a space elevator. A base station would be set up on the Earth's equator, and from there, an incredibly long cable would extend straight up into the sky. The end of the cable would be attached to a weight located beyond geostationary orbit. At an altitude where centrifugal force from the Earth's rotation is strong, on the Earth side, gravity pulls the cable down, while on the space side, centrifugal force, the outward force from rotation, pulls the cable up. By balancing this downward gravity and upward centrifugal force, the cable remains taut and stands upright on its own. In other words, imagine spinning the Earth like a top to keep a string pulled tight and straight. The key is the altitude known as geostationary orbit. Geostationary orbit is about 36,000 kilometers above the ground, where a satellite orbits in sync with the Earth's rotation. An object in geostationary orbit appears to stay fixed above the same point on the ground. Therefore, by placing the cable's center of mass at this altitude, the elevator can be anchored to a specific location. In an actual space elevator design, one end of the cable is fixed to a base on the Earth's equator, while the other end extends far beyond geostationary orbit to about 100,000 kilometers, where a counterweight is placed. There are even proposals to use a captured asteroid as this counterweight. This ultra-long cable would be the lifeline connecting Earth and space. So, how would people and materials be transported along this cable? The answer is a vehicle called a climber. A climber is an elevator car that attaches to the cable and moves up and down, carrying people and cargo to space. It would be electrically powered, with proposed methods including beaming power from the ground via laser or making the cable itself a conductive material to supply electricity. The image is one of a gondola attached to a long, ribbon-like cable, slowly ascending towards the heavens. For example, the concept by Japan's Obayashi Corporation envisions 6 oval-shaped elevator cars, constantly moving up and down, ferrying between a sea-level station and a space station. The travel speed is projected to be around 200 kilometers per hour, meaning it would take about 8 days to reach the geostationary station from the ground. It is certainly not instantaneous, but it would be a slow and safe journey to space, without the violent acceleration or explosion risks of a rocket. In fact, it is estimated that reaching an altitude of about 400 kilometers, the same as the International Space Station, would be possible in about 2 to 3 days. It is astonishing to think you could get to a space station in about the same time it takes to travel from New York to Chicago by train. Theoretically, if this space elevator were realized, we could transport cargo directly to space without using massive rockets. This is expected to dramatically lower launch costs, which are currently enormous. One estimate suggests that the cost to launch 1 kilogram to geostationary orbit could drop from its current $20,000, hundreds of thousands of yen, to as low as $500, or just a few tens of thousands of yen. This is a cost reduction of a different magnitude. Furthermore, since the elevator runs on electricity, it consumes no fuel and is environmentally clean. It truly sounds like a dream transportation system. But the key point is that it is only theoretically possible. The principle of using the balance between Earth's gravity and centrifugal force to anchor an elevator in space is sound. However, being a pipe dream and being able to actually build it are two completely different matters. The single biggest, unavoidable challenge when discussing the space elevator is the issue of materials. Does a cable material even exist that is strong enough to span the distance from Earth to space without snapping under its own weight? In the next chapter, we will focus on this material problem. The greatest obstacle, the material problem, the biggest obstacle to realizing a space elevator is the problem of the cable's material. To create a cable from the ground past geostationary orbit to about 100,000 kilometers would require a material of extraordinary strength. This is to prevent it from snapping under its own weight. It's safe to say that no conventional material meets this requirement. For example, a steel wire would break before you could extend it a few thousand kilometers. It would be unable to support its own mass. Calculations suggest a material at least 100 times stronger than steel is necessary. It must be orders of magnitude stronger and lighter than anything we use in our daily lives. So, what kind of dream material is needed? This is where carbon nanotubes come in. Discovered in 1991 by Dr. Sumio Iima. This material is composed of carbon atoms arranged in a hexagonal mesh structure. This structure is rolled into a tube with a diameter of a few nanometers. A single carbon nanotube is theoretically said to have a tensile strength reaching tens to hundreds of gigapascals. This makes it 50 to 100 times stronger than steel of the same thickness. Expectations soared that this thread of carbon, not unlike a spider's silk, could lift humanity to the stars. It made scientists believe that the space elevator might be theoretically possible with this material. However, the story isn't so simple. Even if a single nanotube is strong, can it be processed into a cable tens of thousands of kilometers long? This is a major hurdle. With current technology, the limit for producing carbon nanotube fibers is only a few centimeters, nowhere near long enough. Furthermore, when nanotubes are joined together to form threads or tapes, the joints become weak points. This prevents the material from exhibiting its theoretical strength. Even a material that is exceptionally strong in theory can see its strength drastically decrease when mass-produced and assembled. Other candidates besides carbon nanotubes are being considered. For example, graphene. Graphene is a revolutionary material for which the Nobel Prize was awarded in 2010. It consists of carbon atoms linked in a hexagonal lattice, forming a sheet, just one atom thick. The strength of a single sheet of graphene is also extremely high, theoretically even greater than that of carbon nanotubes. If you could stack tens of thousands of graphene sheets vertically to create a long ribbon-like tape, that could work. But in reality, the technology to create a single massive sheet does not exist. Other new materials with potential for theoretical strength exceeding carbon nanotubes, such as boron nitride nanotubes, and diamond nanothreads are also being researched. However, all of these are far from practical application. The current reality, as of 2025, is that no material exists that combines the length, strength, and lightness required. Amidst this, some new developments have emerged in recent years. For example, a research team at China's Tsinghua University has reported success in developing a carbon nanotube fiber. It is said that a fiber with a volume of just 1 cubic centimeter can support a weight of 800 tons. The tensile strength of this fiber reaches about 80 gigapascals, far exceeding the standard of 7 gigapascals that NASA once set as a goal. Hearing these numbers alone, you might think the problem is solved. However, the length of this fiber is thought to be at most a few tens of centimeters, nowhere near what is needed. Furthermore, it's unknown whether a uniform strength can be maintained when many such fibers are bundled together. Back in 2005, NASA held an idea contest for a strong space elevator material. Unfortunately, at the time, no one could achieve the target strength, and the prize went unclaimed. As you can see, breakthroughs in materials do not happen easily. Nevertheless, the material scientists around the world continue their efforts. In Japan, joint projects are underway to develop mass production technology for carbon nanotube fibers with specific goals. In summary, the key to realizing the space elevator lies in the development of a dream material. Even with carbon nanotubes, we are currently at a stage where we can only achieve about 1/10 of the required strength. On the other hand, new material research is slowly advancing. If a revolutionary material emerges in the future, providing a clear path, the space elevator project will become much more realistic. But without this foundational material, any grand vision remains a pipe dream. Now, let's assume the material problem is solved. What challenges lie ahead when it comes to actual construction and operation? A mountain of technical and practical hurdles exists. In the next chapter, let's look at some of these real-world obstacles. The real-world hurdles of construction and operation. Let's say, by some miracle, we obtain an ultra-strong material. Even so, there is a mountain of challenges that must be overcome to actually construct and safely operate a space elevator. In this chapter, we will look at 4 major real-world hurdles. 1. Construction, difficulty and cost. The construction of a space elevator would be the largest and longest construction project in human history. With a total length of about 96,000 kilometers, it would require unprecedented processes for launching materials and assembly. First, construction materials and assembly spacecraft would be carried by rocket to the vicinity of geostationary orbit, where they would be assembled to form a base. From there, the spacecraft would ascend to geostationary orbit and slowly deploy the cable down towards Earth. It is a task so immense it's hard to even imagine. Once the cable reaches the ground, climbers would ascend from the Earth, wrapping hundreds of reinforcing cables around the initial one to finally achieve the thickness required. Obayashi Corporation estimates that it will take approximately 25 years from the start of construction to completion. For example, if base construction could begin in 2025, the first material launching rockets would be sent up in 2030, and the geostationary station would open for use in 2050. The total construction cost is estimated at about 10 trillion yen, which is comparable to massive projects like the Maglev train line or the Seikan Tunnel, making it one of the largest projects in history. Of course, it would be difficult for a single nation to bear such an enormous cost. It would need to be an international project. According to a project official, realizing the space elevator will require pooling the world's wisdom to solve many challenges, and multiple technological breakthroughs are essential. In short, new technologies in power, control, manufacturing, and countermeasures for the space environment must be developed. It's a field full of unsolved problems. 2. The risk of space debris and meteoroid collisions. Space is filled with the remnants of satellites and rockets launched by humanity, floating as debris. The number of these objects is countless, and they orbit the Earth at speeds of several kilometers per second. If this debris were to collide with the space elevator's cable, the thought alone is terrifying. Even a small bolt, hitting at high speed, could puncture the cable or, in the worst-case scenario, sever it completely. The orbits above 2,000 kilometers are particularly dense with satellites and debris, posing a significant collision risk. Furthermore, natural meteoroids are also flying through space, and protective measures might not be sufficient for long-term operation. As countermeasures, ideas include making the cable a ribbon shape so that a partial tear doesn't lead to a complete break, or collaborating with debris-tracking satellites to clean up the orbital environment. However, the region above geostationary orbit spans the entire globe, so protection has its limits. A means of repairing the cable in case of damage must also be planned in advance. Proposals include having spare cables ready for replacement, or equipping climbers with repair robots for constant patrols. But all of these present their own set of challenges. 3. The influence of atmosphere and weather. Since the cable will extend from the ground, through the atmosphere, and into space, it cannot avoid the effects of weather. First, there's the issue of wind. While the equator is relatively free of large typhoons, there are strong jet streams at higher altitudes. Although the cable is thin, the entire 100,000-kilometer length, catching the wind, would cause unimaginable vibrations. If the cable sways significantly, it would interfere with the elevator's ascent and descent. For this reason, one proposal is to build a mobile, floating base at sea, allowing for some adjustment of the cable's position. In Obayashi Corporation's concept, a disc-shaped floating base, about 400 meters in diameter, called the Earth Port, would be placed at the equator. The cable's tension would be regulated and anchored using the weight of seawater. The idea is to control the cable to prevent resonance during strong winds by slightly moving the base itself. However, this would not be a perfect solution. Next is the problem of lightning and electromagnetism. Extending a metallic cable vertically would act like a lightning rod, attracting strikes that could send massive currents through the system. Countermeasures such as covering it with an insulator or designing a grounding system to withstand lightning strikes are necessary. Furthermore, the material degradation caused by atomic oxygen cannot be ignored, as the space elevator cable would be exposed to it. Other environmental factors, such as the effects of ultraviolet and cosmic rays, and expansion and contraction due to temperature changes, are also challenges. 4. International cooperation and legal frameworks. Even if all technical challenges are solved, there are still legal and international cooperation issues. First, the space elevator extends from Earth into outer space. But outer space cannot be claimed by any country. So, who owns the elevator's cable and space station? their legal status is ambiguous. Also, the location of the ground-based anchor is a problem. The land areas closest to the equator are limited to countries like Indonesia, Ecuador, Kenya, and Brazil. Placing a base in one of these countries would raise issues of sovereignty and national security. Conversely, the idea of a floating sea base in international waters would require international management, belonging to no single country's jurisdiction. In addition, the enormous cost of construction would necessitate funding and cooperation from multiple countries. Even the International Space Station was only realized through the collaboration of the United States, Russia, Europe, Japan, and others. Political and economic challenges, such as coordinating the interests of participating nations and distributing profits, cannot be overlooked. These are just the major hurdles. There is a vast number of other issues to consider, such as climate control, safety during the multi-day ascent, and cable maintenance. Realization will truly require the collective wisdom of the entire world. If it were realized, the future of society and space development. So far, we've looked at the dream and the challenges of the space elevator. But what if it were actually realized? How would humanity's future change? In this chapter, let's consider the impact of the space elevator from multiple perspectives. A dramatic reduction in transportation costs to space. Currently, the cost of launching satellites and supplies with rockets is several thousand to tens of thousands of dollars per kilogram. We live in an era where a single large rocket launch costs hundreds of millions of dollars, and sending one astronaut to the ISS costs tens of millions. With a space elevator, because it would simply use electrical energy to run a motor, transportation costs would become orders of magnitude cheaper, while specific numbers vary. As mentioned earlier, some estimates suggest the cost per kilogram could fall not just to a few $100s, but to as low as a few dollars. In an extreme sense, we can even envision a future where traveling to space costs about the same as a train ticket between major cities. If costs were reduced by a factor of 100 or more, numerous space projects that have been economically unfeasible could become possible. For example, space-based solar power satellites, large-scale space telescopes, and the assembly of large structures in orbit. Projects that have been bottlenecked by exorbitant costs would suddenly move forward. The popularization of space tourism and space hotels. If a space elevator were built, space travel would become far safer and more affordable. Travelers would avoid the dangers of a rocket launch. And from a medical standpoint, the slow ascent would reduce the physical strain caused by rapid changes in gravity. Tourists could board the elevator and spend several days leaving Earth, enjoying a space journey, much like a luxury cruise. An orbital hotel could be built at the geostationary space station, where guests could dine in a restaurant while gazing at the round Earth or enjoy zero-gravity sports. While private space travel is already beginning, the era of the space elevator could trigger a mass popularization of space tourism, making it not just something for the super-rich, but a once-in-a-lifetime trip for ordinary people. Expansion of space infrastructure. The existence of a space elevator would allow for the continuous transport of large quantities of materials into space, enabling the construction of various infrastructures in orbit. For example, the geostationary station itself could become a massive platform, hosting space factories and research facilities. Industrial applications, such as manufacturing new materials in a zero-gravity environment or conducting research on semiconductors and pharmaceuticals, would become promising. Furthermore, by releasing objects from the space elevator at a higher altitude, they could escape Earth's gravity well without using extra fuel. This would also be advantageous for planetary exploration. By detaching a spacecraft from a point beyond geostationary orbit, say at 100,000 kilometers, it would leave Earth's orbit and could be set on a trajectory to the Moon or Mars. In other words, the space elevator could become a hub for space routes originating from Earth, a gateway for deploying satellites into low Earth orbit could also be established on the elevator by carrying a satellite up from the ground and gently releasing it at an altitude of around 300 kilometers. It could be placed directly into a low Earth orbit. An era where satellites can be deployed without rockets would lead to the expansion of communication and observation networks, synergy with Moon and Mars, colonization plans with a space elevator. Plans for colonizing the Moon and Mars would become much more realistic. First, since materials and personnel could be transported cheaply to orbit, large lunar or Martian colonization ships could be assembled there, allowing for the transport of massive amounts of supplies at once. Currently, due to the limitations of rocket launch capacity, we can only send small probes multiple times. But in the elevator era, the idea of building a colossal spaceship in orbit becomes feasible. In the future, it might even be possible to build a space elevator on the Moon. The Moon's gravity is only 1/6 that of Earth's, and it has no atmosphere. So it's said that an elevator connecting the lunar surface to lunar orbit is theoretically possible even with existing materials like aramid fibers. If a lunar elevator were built, a logistics chain could be created where resources are lifted from the lunar surface, sent to a lunar orbital station, and then transported to Earth. Mars, with a gravity about 1/3 of Earth's, presents more of a challenge due to its fast rotation and large geostationary radius. But a similar concept is envisioned for the future. In any case, an Earth-based space elevator would be the infrastructure that strongly supports our full-scale expansion to the Moon and Mars, resource mining, and impact on Earth's civilization. Another noteworthy aspect of the future opened up by the space elevator is the utilization of space resources. In recent years, the concept of asteroid mining, extracting rare metals and hydrogen from asteroids, has gained attention. However, the cost of bringing those resources back to Earth is extremely high, creating a hurdle for practical application. With a space elevator, it would be possible to bring resources from an asteroid to a location near geostationary orbit and then lower them to the ground via the elevator. For example, if water or rare metals could be delivered to Earth cheaply, it could help address the problem of resource depletion. Alternatively, resources mined off-world could be processed at a space station and used for space infrastructure without ever being brought down to Earth. The space elevator would become a major artery for logistics between Earth and space, holding the key to opening up a true space-based economy. Furthermore, its impact on the energy problem cannot be ignored. The space elevator concept also includes plans to install a space-based solar power system in geostationary orbit, with the generated electricity transmitted to the ground via microwaves in space. Solar power generation is possible continuously, unaffected by weather or nighttime. It's estimated that the energy received by a 2-kilometer square solar panel in space is equivalent to the total annual energy consumption of all humanity on Earth. The space elevator would contribute to the installation and maintenance of these giant panels and receiving antennas. If this concept were realized, It could open up the possibility of a limitless supply of clean energy for Earth, potentially even solving humanity's energy problems, from space travel to industry, resources, and energy. The space elevator could be a game changer for Earth's civilization. The future it could bring is so dynamic, it would overturn our current common sense. Our relationship with space would change dramatically. The impact of space becoming not a special destination, but a place one can visit casually, is immeasurable. The space elevator is not merely a transportation infrastructure. It is a colossal project that would have ripple effects on human society, economy, and culture. However, while we dream of such a rosy future, when we look at reality, the hurdles remain high. So, will the space elevator truly be realized within our lifetimes? In the 21st century, in our final chapter, based on the latest research and development trends, let's consider the realistic possibilities and future predictions. Reality and future predictions. So, what is the reality as of 2025? Unfortunately, we are still just at the starting line. The consensus among experts seems to be that while a space elevator is not theoretically impossible, its practical implementation within this century is extremely difficult. Regarding the biggest challenge, material development, research continues in countries around the world. As mentioned earlier, a recent achievement was the report from the Tsinghua University team in China, which created a carbon nanotube fiber with a groundbreaking strength of 80 gigapascals. This was a dramatic improvement over previous materials and raised hopes for a space elevator material. However, this fiber is still very short, and the technology to manufacture a cable tens of thousands of kilometers long from it does not yet exist. Also, it's been pointed out that the 7 gigapascal strength target, once proposed by NASA, would require a much higher strength in practice to account for safety factors. Ultimately, construction cannot begin without the emergence of a perfect material. So, it's no exaggeration to say that the timing of a breakthrough in material research will determine the timeline for the space elevator's realization. So, what about the development plans of various countries and companies? Japan's Obayashi Corporation announced in 2012 its goal of completing a space elevator by 2050 and presented a rough timeline. However, as of 2025, concrete construction has not yet begun, and it remains in the research phase. Some media reports have mentioned a 2025 start date for construction. But in reality, with both materials and technology still immature, we are not in a position to begin construction anytime soon. However, Obayashi is steadily laying the groundwork by conducting practical experiments with carbon nanotubes in collaboration with universities and companies, and by presenting its concept at space-related exhibitions in Japan. Other groups, primarily Shizuoka University and the Japan Space Elevator Association, are also conducting small-scale experiments. In 2018, a space elevator experiment using a microsatellite from Shizuoka University was conducted in a world-first attempt. They tried to move a miniature elevator model along a tether connecting two microsatellites deployed from the International Space Station. The experiment confirmed that the elevator could move in a microgravity environment, providing valuable data for the future. Although miniature in scale, this was the first attempt to operate an elevator in space and can be considered a steady step forward. NASA in the United States also showed interest in the space elevator in the past. holding an advanced concepts workshop in the late 1990s and compiling a report. It concluded that while construction would be difficult for the next 50 years, it was worth researching as a future infrastructure. In the 2000s, NASA and private organizations hosted climber competitions and strong tether contests, known as the Elevator Games. These were intended to stimulate technological innovation with prize money. But at the time, none produced decisive results, and the competitions were discontinued. Since then, NASA itself has focused more on cost reduction through reusable rockets, such as the Space Shuttle and, more recently, SpaceX's Starship program. It could be said that their stance is that advancing rocket technology is the more realistic goal for now. With the elevator being a long way off, SpaceX founder Elon Musk has also expressed a skeptical view of the space elevator. He has stated, "It would be great to have a space elevator, but honestly, I don't think it's realistic. It would be easier to build a bridge from Los Angeles to Tokyo, which is about 3,000 miles or 4,800 kilometers. We don't even have a good carbon nanotube rope yet, let alone an elevator that's 60,000 miles, or about 100,000 kilometers long." It's a rather harsh opinion, but perhaps because Musk is achieving results with cutting-edge rockets, he has a keen sense of the gap between that and the current level of technology. He did add that he would be happy if someone proved him wrong. So, he is not completely dismissing the possibility of its realization. Meanwhile, China has also shown interest in the space elevator. The China Academy of Launch Vehicle Technology announced a plan in 2017 to operate a space elevator system by 2045. Russia and Europe also have small but active research communities, and information exchange and annual conferences are held through organizations like the International Space Elevator Consortium. These organizations are closely monitoring developments in materials and related technologies, while carrying out preparatory work such as conceptual design and standardization. In summary, the general assessment is that realization is not zero, but achieving it within this century, by around the year 2100, is overly optimistic. Even if a miraculous breakthrough in materials were to occur in the 2030s, considering the subsequent design, testing, international coordination, and construction, even a 2050 completion date for the first elevator would be highly ambitious. Indeed, while Obayashi Corporation aims for 2050, the company itself comments that numerous technological breakthroughs are necessary and that realization is still a long way off. On the more pessimistic side, some believe it will still be difficult even in the 22nd century. However, just as it was thought impossible for humans to go to the moon 100 years ago, scientific and technological progress sometimes exceeds our expectations. For the space elevator, too, a sudden material revolution or a groundbreaking idea could change the situation entirely. The important thing is the fact that the dream of a space elevator is driving researchers around the world right at this moment. The will to overcome the impossible, because it is theoretically possible, is leading to the development of new materials and the refinement of related technologies, even if it is not realized. The byproducts obtained in the process, such as the practical application of ultra-strong fibers or improvements in laser power transmission technology, will also be beneficial to industries on Earth. The act of chasing a dream can itself promote scientific and technological advancement. Now, finally, I would like to conclude by summarizing what the space elevator means to us as humanity. And will the day come in our generation when we can ride an elevator to space? Let's end with that question. Conclusion. The space elevator. It is not just a massive project, but a tower of dreams that symbolizes humanity's endless curiosity and ambition. This concept, first envisioned by Tsiolkovsky in the 19th century, expanded upon by Clarke in science fiction, and now being pulled into reality by 21st century scientists, can be said to be the very embodiment of humanity's challenge to make the impossible possible. Certainly, the technical hurdles are high at present, and we cannot be optimistic. But just as airplanes were born in an era when flying was a fantasy, and humanity stood on the moon in an era when moon travel was a dream, great dreams can sometimes become the driving force that moves reality. The dream of the space elevator will also inspire scientists, engineers, and the societies that support them, ultimately leading to new technological innovations, even if we do not see its completion in our generation. As long as this dream is passed down to the next generation, and the one after, the day may come when an elevator to space appears on the horizon. If the space elevator is realized, human civilization will take a giant leap into the cosmos, and the boundary between Earth and space will become much lower than it is today. The space elevator project involves not only physics and engineering, but also challenges in economics, international cooperation, and law. The process of overcoming these comprehensively is also a grand drama of humanity, uniting to open up a new frontier. This struggle between dream and reality is the unique charm of the space elevator theme. Finally, a question for all of you watching. Will the day come in our generation when we can travel to space by elevator? No one knows the answer yet, but as long as we continue to pursue that question, humanity will continue to climb the ladder to space, one step at a time. As long as the incredible dream of the space elevator continues to be the driving force that moves us forward. Thank you for watching until the end. If you found this video interesting, please be sure to subscribe and give it a high rating. Also, this channel, Cosmic Lab, has been able to grow steadily thanks to the support of all our viewers. Thank you so much for your continued support. We have set a challenging goal of reaching 100,000 subscribers by the end of 2025, and we are working our hardest every day to produce videos. If you haven't subscribed yet, we would be delighted if you would subscribe and continue to support us. We'll be waiting for you in the next video.